Jamb 2026 candidate, you all are welcome to today's lecture. Remember, we are still treating the Jamb syllabus physics, and our topic for today, we are continuing with magnets and magnetic field. So do well to get your pen and your notebook to jot down whatever you understand in this lecture, and also be aware that the soft copy of this lesson material, this lesson notes, are available. If you need any of the lesson notes, we have all of them in our library. So send me a DM to get access to our library. All right. So magnetic field, all right, and magnets. We have to understand the concept of magnetic field and magnets. So what is magnets? Magnets is that which bring about a magnetic field. So magnets bring about magnetic field. What is magnetic field? It's an area not requiring touch where magnetism can be felt. All right, an area, a region where magnetism, the magnetic effect, the effect of magnetism, attraction of a magnet can be experienced. All right. Magnetism is an area or region where the attraction or the repulsion of a magnet can be felt. Now let's look at the natural versus the artificial magnets. Under the natural magnets, we have the lodestone. You know the lodestone now, that black magnet you see. All right, that black magnet, that's lodestone. All right, and we have the artificial magnets, which is the bar magnet and also the horseshoe magnet. All right, both of them are the artificial magnets. Now, what are the properties of magnetic material? What are the properties of magnetic material? So magnetic material are material that can be used to make magnets or material that can be attracted by a magnetic field. All right. So for soft iron, okay, soft iron magnetize easily. So you can bring about magnetic induction in soft iron easily, and it also loses magnetism easily. Soft iron magnets. All right. Then steel retains magnetism. That's the difference between the soft iron magnet and the steel. Steel retains magnetism for a long time. All right. So it's easy to magnetize iron, and it loses its magnetism so quick, but it's harder to magnetize steel, and steel retains magnetism for a long period of time. Making versus demagnetization. That's making magnets and demagnetization. And how do we make magnets? We make magnets by stroking with magnets. When you stroke a metal, such as iron or steel, with magnets, magnetism is formed, or an artificial magnet is formed. All right. So the method of demagnetization, that's to break magnetism in an object or a substance, is through heating or hammering. Or you can also pass an alternating current through the material or the substance to demagnetize. So to magnetize, you can either use stroking with a magnet to magnetize. You can also use direct current to magnetize. But to demagnetize, you use heating. You heat the magnet, or you hammer it, or you use alternating current to demagnetize it. All right. This is magnetic field. All right. This is magnetic field. Let's look at each. The first we have here is horseshoe magnet. You can see the shape of horseshoe magnet. It has the north pole and the south pole. All right. Where you have the north pole and the south pole, they attract, okay, where you have them, but they repel where you have similar poles, okay. Horseshoe magnet is that magnet that is like you, okay, it's like you. That's the horseshoe magnet. All right. So remember that in magnetism, like pole repel, unlike pole attract. So you have two poles. You have the north and the south pole. When the north pole and the south pole faces, they attract. All right. But when the north pole and the north pole faces, they repel. When the south pole and the south pole faces, they repel. This one is magnetic field in a solenoid. All right. Magnetic field in a solenoid, a coil instrument. All right, this is the magnetic field. You can see it. It flows in and it flows out, depending on where you have the north and the south pole. All right, but all you have to know is that like pole repel, unlike pole attract. So this one is the magnetic field of the Earth to the south pole, not south. From the north pole to the south pole, you can see how unlike pole attracts. All right, so this is the bar magnet. All right, you can see the bar magnet. Okay, so here is the north, here is the south. You can see how the north pole attracts the south pole. You can see the flow enters the south pole. But from north to north, it cannot attract. South, it can't attract. So what are the methods to keep magnetism? How do we protect magnetism? You know, magnetism can be lost. So we need to employ, techniques to protect magnetism, okay, to conserve magnetism, okay. The first we have is store magnets with keepers. And what are magnetic keepers? Magnetic keepers include soft iron strip. Soft iron strip, those are magnet keepers, all right. Avoid heat, keep the magnet away from heat. Hammering or dropping, prevent all this from the magnets. Don't allow the magnet to be heated or hammering or dropping. No. So to conserve your magnet, store it with magnetic keepers or magnet keepers. Then also avoid heat, hammering or dropping the magnet. All right. Magnetic flux pattern of isolation. Flux pattern of isolation magnet. What is flux pattern? Flux pattern is how the magnetic field, the pattern of the magnetic field. That's flux. Flux is that magnetic field. Okay. That magnetic field. That's flux. All right. So what is the magnetic pattern or flux of isolated magnet? The flux pattern of isolated magnet is lines emerge from north, curve and enter south. So like the one we just saw, okay? Lines emerge from north. For example, this magnetic field of the Earth now, lines emerge from the north like this, then connects to what? South, all right? unlike pole attracts. All right, so you can see how it occurs. Flux pattern of an isolated magnet. Lines emerge from north, curve, then the curve can't enter south. Okay, like what I just illustrated. So what is the flux pattern exhibited when two magnets are placed together, pole to pole? What is the flux pattern? The flux pattern is that like pole repel, flux line pushes apart. So when the pole is like, you have north for example, or south for example, the line pole repairs. So the line is not going to join, okay? It's going to repair. Instead of it to join like this, you are going to see something like this, okay? They'll go their own way. For example, let me show you something. Look at what we are talking about here. It's something like this, okay? It's something like this. So here you can see, instead of this one from this north end to join this one from this north end, you can see what is happening. Okay, this one they go their own way. They don't rejoin. They hit each other because they are alike. Why unlike poles attract? All right. So when you bring two magnets together, pole to pole, unlike pole we attract. So south we attract north pole, or north we attract south pole. Okay. So how do you know that north pole attract the south pole, or how do you know that the north and south pole attracts? Okay. Or how do you know that the unlike pole attracts? Because the flux line we join. Okay. For example, look at this flux line now. See where the flux line joined here. North. You have north here. North here. You have south here. You can see how the flux line joins. Okay, it joins. All right, when you place two magnets pole to pole. All right, what is the flux pattern in a current carrying conductor? All these things, Jamb, say make you know. The flux pattern formed is a concentric cycle around the wire. So the flux forms a concentric circle around the what? A wire. A concentric circle is just like a current circle. Okay, a concurrent circle around the wire. What is the polarity? The polarity is tested using a right-hand rule. So the polarity of a current carrying conductor is tested with what? Fleming right-hand rule. Right, Fleming right-hand rule. All right, for a current carrying conductor. Let's look at the flux pattern of a current carrying conductor. So this is the flux pattern of a current carrying conductor. You can see the flow. Concentric, okay, you can see it. Magnetic flux pattern of a current carrying conductor. So this one is the magnetic flux. This round thing with here. You can see the pattern. Concentric in a concurrent circular pattern. Okay, you can see the direction of the current. Now be this, so this arrow. This one is the conductor. So this one is the magnetic flux. All right. Now let's look at the Fleming right-hand rule used to test the polarity. Okay, whether it's the north pole or is the south pole, or how to know the direction of the magnetic field and the direction of the current. This is Fleming's right hand rule. All right, you can see it. It's right hand facing the right, just like this. Now so it be, okay, like this. Don't forget, it's like this. Fleming's what? Right hand rule. And the thumb shows the direction of what? The motion. Why the what? The forefinger, which is this one, shows the what? The direction of the magnetic field. Why this one? The second finger, that's this longest finger, shows what? The direction of the current. That's why when I showed you that conductor just now, the conductor here now is the direction of the current. That's what that hand, this long hand represents, okay? The direction of the current. Here, this one is the magnetic field. Look at it. It's this hand that represents it. So when you put a Fleming right hand rule here now, for example, you are going to see that, you are going to see it. So motion, the magnetic field, and the current. All right. Now let's look at the flux pattern of a circular wire. So it's just like a wounded coil. For example, a circular wire, when a wire is wound around a conductor, all right? What is the flux pattern of this circular wire? Flux loop around the wire, stronger at center. The flux loops around the what? Wire, stronger at the center. It loops. You know what is a loop now? Loop, to form you with something, around something, to tie something around something. That's loop, all right? And it's stronger, the flux is stronger at the center. Let's take a look at the diagram. So this is the diagram of the flux pattern in a circular wire. You can see it loop. Can you see how it loops around? You can see this one is the circular wire. Okay, this is the wire, circular wire. All right. So this one is the flux. You can see how it loops around the two circular wire, and the flux is stronger at the center. Around here is stronger around here. You can see how it loops around the two wire. It loops around the two wire. Okay, circular wire. So it loops and it's usually stronger at the center. Now let's look at the flux pattern of a solenoid. All right, a solenoid. In a solenoid, the flux pattern is uniform. Flux resembles a bar magnet. One end acts as north pole, the other end as a south pole. I showed you a bar magnet not quite long ago. So as that bar magnet's own be, one end will act as north pole, the other end as south pole. All right. How is the polarity determined? The polarity is determined using the same what? Fleming right hand rule. Okay, for what? Solenoid. Let's look at the diagram showing the flux pattern of a solenoid. Remember, how does the flux pattern look? It's uniform and flux resembles a what? A bar magnet. So anytime you remember the flux pattern of a bar magnet, just know that it's the same flux pattern that you have in a solenoid. This is the flux pattern of a solenoid. One point acting as the north pole, that's here. The other point acting as a south pole, okay? Just like a bar magnet, okay? Magnetic field is uniform from one pole to another. So current enters through here and goes out. So the magnetic field, it passes from the north pole to the south pole, exactly how the bar magnet is, all right? So this is a solenoid coil. All right, so hope you know the function of a solenoid. What solenoids are used for? Solenoid is a kind of coil that are used to provide, motion Okay, it's used to provide motion. Okay, it's used in electric motor. It's used where motion is needed. Okay, that's where you use solenoid. All right, it's used in electric motor. It's used in electric belts too. So you use solenoid. Solenoid is applied in a lot, even in alternators. Okay, you have solenoid in some alternators and so on and so forth. So where motion is needed, all right, mechanical energy is needed. That's where you use solenoid. Solenoid produces motion, or it induces motion through electromagnetism. When you induce electricity into the solenoid coil, it generates a magnetic field. So that field, because of that attraction by the north and the south pole, it brings about mechanical energy. It brings about what? Motion and movement. So that's how the solenoid functions. Okay, that's the principle at which the solenoid functions. Remember, it's what? Uniform, and it resembles that of a bar magnet. You can see how uniform it is. Okay, from north to south, from north to south. Remember, the flow of magnetism is usually from north to south pole. You can see the flow. Look at the arrow from north to south. From what? North to what? South. The polarity is also tested with Fleming's right hand rule. You know that in the Fleming's right hand rule, the thumb represents what? The motion. This one represents what? The magnetic field, while this finger represents what? Direction of current. Okay, when you looked at that solenoid just now, you will notice that this place, the center, is the direction of the current. Okay, that was where the current was induced into the solenoid. All right, so let me show you. So this is the direction of the current, this center. Okay, the current enters through here. Okay, and the current moves like this. So this center is where you have the current that induced this magnetic field. Now let's look at the flux pattern of the magnets placed in Earth's field. The flux pattern of the magnets placed in Earth's field is a kind of flux that aligns with the Earth's magnetic line. So it's just the same as the Earth's magnetic line. The same thing with the Earth magnetic line. You have north pole down, have south pole here, and the flux flow in between from north to south pole. From north to south pole. It connects from north to south pole like this. Just like the Earth. It mimics the Earth magnetic line. Let's look at it. So this is the magnetic flux generated by an object placed on the Earth's field. All right, this one is the Earth's field. Okay, you can see the north pole, you can see the south pole. It flows from the north flux into the south pole, just like that. The two sides, from north to south, from north to south. Okay, so here is the southern pole of the magnet. So the part that is the south pole of the Earth is where you find the north pole of the magnet. The part that is the north pole of the Earth is where you find the south pole of the magnet. Remember, unlike pole repel, like pole attract. So in the Earth magnetic field, since we have the north geographic pole here, all right, that's where we are going to have the south pole of the magnet, because it's going to be the south pole of the magnet is going to be pulled towards the north pole of the Earth. All right, to attract. All right, so that's why you have opposite pole of the Earth. You have opposite pole of the magnet. That's where the opposite pole of the magnet forms. So this is a diagram showing all the flux pattern in various conductors and various medium. All right, okay. This one here is in the circular wire. Okay, what happens? The flux loop around it. This one is a solenoid. It's uniform and it resembles that of a bar magnet. One part acting as the north pole, the other part here acting as the south pole. That's where the current flows. Left, you have the north pole here. The right, you have the south pole here. All right. So it all depends. Any part can act as the north and the south pole in a solenoid. Okay, but just know that one part acts as the north pole, the other part as the south pole. So this one is for the object placed in the Earth magnetic field. Okay, it carries the magnetic field of the Earth. Okay, where you have the north pole and the south pole, depending on where the geographical pole of the Earth is. The north geographical pole of the Earth is here. Okay, for example, you are going to have the south pole of the magnet here. But this diagram we see here, we have north pole up here and we have south pole below. So this shows that the geographical pole of the Earth is here. The south geographical pole of the Earth is here. That's why you have the northern pole of the magnet here. So below here is where you have the northern geographical pole of the Earth. That's why you have the south pole of the magnet here. So the flux flows from the north pole to the south pole. Remember the flux pattern in a current carrying conductor field. The Earth magnetic field from north to south poles, magnetic meridian, is measured with a compass. And still under the Earth magnetic field, you have the angle of dip. Okay, angle of dip is known as what? Angle of inclination. Okay, which is an angle to the horizontal. An angle to the what? To the horizontal. This angle like this, that's the angle of dip to the horizontal. That's angle that faces the horizontal. You also have angle of declination. Okay, is angle to true north pole. The angle to the true north pole is the angle of declination. The angle to the true north pole is the angle of what? Declination. The angle of dip or angle of inclination is the angle to the horizontal. All right, put that inside your head. The angle of declination is the angle to the true north pole, while angle of dip or angle of inclination is the angle to the horizontal. Okay, now this symbol you have here, okay, this one is the symbol of tan, okay, and this is flux, is the symbol of flux. So anytime you want to remember the symbol of magnetic flux, just remember tan. All right, tan in SOHCAHTOA. So that's the symbol of flux. All right, so B times A for magnetic flux, B times A, that's the formula for magnetic flux, where B is equal to flux density, and the SI unit of magnetic flux density is Tesla. That Tesla, well, you know, so okay, Elon Musk Tesla. That's the SI unit for magnetic flux density. Okay, so the magnetic flux density varies with latitude. Maximum at poles. So magnetic flux density is what? And it is maximum at pole. What is latitude? Okay, what is latitude? You know, we have latitude, we have longitude. Latitude is the location of an object in the geographical pole. All right, that is latitude. The location of an object in geographical pole. Okay, usually measured with compass. Latitude. All right. So this SI unit Tesla is the SI unit of magnetic flux density. While the SI unit of magnetic flux itself, magnetic flux, is Weber. So the SI unit of magnetic flux is Weber, while the SI unit of magnetic flux density is Tesla. All right. Now let's look at the magnetic flux formula. Magnetic flux is equal to B times A times cos theta, where cos is the angle, depending on the angle. Is it angle of dip? Is it angle of declination? What is the angle? What is the angle given to you? Okay, where this thing that's like tan is equal to the magnetic flux. Okay, the SI unit is Weber, measured in Weber, just like I told you, WB. B is equal to magnetic flux density, measured in Tesla. The SI unit is Tesla. A is equal to area through which flux passes, measured in meter square. All right. Most of the time, the SI unit of area is meter square. All right. Then theta is the angle between magnetic field and normal to the surface. Between the magnetic field and the normal. The normal is the area where there is no magnetic field felt. Okay, that's the normal. The normal to the surface and normal to the surface. That's the normal, the area where that's the angle between the magnetic field and the area where magnetism is not felt. All right. So that's the angle. So the formula for magnetic flux is magnetic flux equal to B, which is magnetic flux density. B times A times cos theta. Okay, depending on the angle that was given, you substitute and you get your answer. Remember, the angle of dip or angle of inclination is the angle to the horizontal, while the angle of declination is the angle parallel to what? The true north pole. All right. Magnetic flux density varies with latitude, and I explain what latitude is to you: the location of an object in a geographical pole, measured with compass. All right. So maximum flux when field is perpendicular, theta is equal to 0 degrees. When field is perpendicular, the maximum flux theta is equal to 0 degree. Okay, cos theta is equal to 1. So cos theta is equal to 1. So the cos of the angle is equal to 1 at maximum flux. When flux is maximum, cos theta equal to 1. So in your question, maybe they give you a calculation question and they tell you that the magnetic flux is maximum at so just know that this your cos theta is equal to 1. All you have to do is just times A times B and get your answer. Because anything times 1 is equal to that thing. So forget about the cos theta. Just times A times B, you get your answer. Okay? So at maximum flux, theta, which is the angle, is equal to 0 degree. Okay, 0 degree. Cos 0 is equal to 1. That's what you have here. It's the same statement. All right. So at 0 flux, okay, that's when there's no flux. That's as the maximum flux, highest flux, we get this. Theta is equal to 0. Okay, so cos theta will now give you 1. What is cos theta? Cos theta is 1 now. So at 0 flux, when magnetic field is parallel, theta is equal to 90 degree and cos theta is equal to 0. What is cos 90? Is cos 90 0? Theta is equal to 90 degrees. So cos theta equal to 0. Variation of Earth's magnetic field. Okay. The Earth's magnetic field changes with latitude, longitude, and time. Just know that these are the things that affect the Earth's magnetic field. It varies with latitude. I already explained what latitude is to you. Longitude and also the time. So you know what time is already. And longitude. What is longitude? Take that as your assignment. Okay. I already told you latitude. You go and find the meaning of longitude. All right. So all of them, they all deal with the geographical pole. Object in the geographical pole. Okay. This latitude deals with the location of the objects around the equator. Okay. Around the equator. In the geographical pole of the Earth, usually measured with a compass. All right. So this is for latitude. So you go find the one for longitude. So just know that the Earth's magnetic field varies with latitude, longitude, and time. So angle of dip equal to 0 degrees at equator, while it's 90 degrees at poles. So at the equator of the Earth, angle of dip is equal to 0 degrees, while at what? At the poles is equal to 90 degrees. All right. So just know that when you are calculating, when you are solving magnetic flux density. Okay, so you all know that the theta can either be 0 or 90. It can either be 0 or 90. So if you are in your exam hall, you don't remember. Okay, you don't remember all these things. First of all, try 0. If you try 0 solve, you see the answer for the options. Among the options, you mark your option. But if you try 0 solve, finish. That's cos 0 degree. Cos 0 is what? Or cos theta is what? So if you try 0, if you use 0 to solve, you don't get the answer. Try cos 90. Then you will get the answer. You pick your correct answer, come out for there. So what is the application of the Earth's magnetic field? It's applied in navigation, where compass is used for navigation. Okay, compass shows us the north and the south pole of the Earth and so on and so forth. So it's also applied in surveying. All right, it's also applied in geophysics, magnetometer, and protecting against solar winds. Now that we have understood magnetic field, magnets, types of magnets, how to magnetize or demagnetize, application of magnets, and magnetic flux pattern in various substances and objects, let's now take some Jamb must repeat question to test the knowledge we've acquired so far and also measure our preparedness for Jamb UTME 2026. Jamb must repeat questions. Question 197. Soft iron is used for what? A. Permanent magnets. B. Temporary magnets. C. Demagnetizing. D. Earth's core. What's the answer? Drop the answer in the comment section. Very easy question. Question 198. Magnetic field line what? A. Starts at S pole, which is South pole. B. Starts at North pole. C. Are straight. D. Never cross. What's the answer? Drop the answer in the comment section. Question 199. The Earth's magnetic dip, that's the angle of dip, is what? A, at 0 degrees at poles. B, at 90 degrees at equator. C, angle to magnetic north. D, angle to horizontal. What's the answer? Earth's magnetic dip is what? The angle of dip of the earth is what? I emphasize on this. Please drop the answer in the comment section. Solenoid polarity is determined by what? A, Fleming right hand rule. B, Fleming left hand rule. C, Ampere's law. D, Ohm's law. What's the answer? Drop the answer in the comment section. Question 201. Magnetic flux density is what? A, this over this. B, that over that. C, this times this. D, this plus this. What's the answer? Drop the answer in the comment section. I swear this question is too easy. It's so easy. So easy.